In this video we're going to introduce the binomial model, and it falls under the heading of a Bernoulli trial in the same way that the geometric model did, but they answered two different questions. What is common to both of them is what I've listed here, and this is just a reminder of what the properties of Bernoulli trials are. So again, there are only two possible outcomes on each trial, the success or failure. In advance, the probability of success is the same every trial, and as you proceed, the trials are independent. In other words, the outcome of each trial has no effect on the other trials. So let's look at an example and see if we can start to get a feel for how the binomial model is going to be different than the geometric that we've looked at already. So we're going to examine the same problem we looked at last time, but we're going to ask different questions. So this, again, just a reminder, a cereal manufacturer puts pictures of athletes in cards in boxes of cereal, and 20% of the boxes have Tiger Woods, and the rest have David Beckham or Serena Williams. Now, what we were asking in the situation involving a geometric model was, how many boxes should I expect to open before I get one that has Tiger Woods? In other words, I was waiting for that one Tiger Woods card, and then I was going to stop. So anytime you're waiting for something to happen, that would be a Bernoulli trial situation, but it would be geometric. Notice the difference in what we're asking here. You decide to open 5 boxes. What's the probability you get exactly 2 pictures of Tiger Woods? So, again, the distinction here is that we're not waiting to get a Tiger Woods card. What we're doing is we're just going to open 5 boxes, and we want to know what the probability is that we get exactly 2. Okay? So, we're saying let x equal the number of successes. So let's define what a success is. Success, we mean to get a Tiger Woods card. Alright, so therefore the probability of success, or our P, would be 0.2, and failure would be if we don't get a Tiger Woods card. So that's our Q, which would be 0.8. Okay, so far so good. Now what I like to do is I like to put my 5 boxes out in a row. So here's my 5 boxes. 1, 2, 3, 4, 5. And again, notationally, we're interested in, I'll write it over here, we want the probability that x is equal to 2. So we've got 5 boxes, and for 2 of them to have Tiger Woods pictures, that would mean that, any 2 of these boxes is going to have a Tiger Wood card in them, but only 2. So let's just say the first 2 I open have Tiger Woods. So I'm going to put T for Tiger, T, T. So those have Tiger Woods, and then I'm going to put this symbol. That means not a Tiger Woods, not a Tiger Woods, and not a Tiger Woods. So the probability of getting a Tiger Woods card in the first box is 0.2, in the second is 0.2, and then Tiger Woods, non-Tiger Woods card in the second or the last 3 would be 0.8 for each. So that might suggest that the answer is just, well, 0.2 times 0.2, so 0.2 squared times 0.8 to the third. So I'm going to start by writing that down. 0.2 squared times 0.8 cubed. And now you might think, well, that's the end of the story, because we just did it, right? We just figured out the probability that 2 boxes have Tiger Woods cards and the other 3 don't. However, we actually didn't completely find what the question was asking, because what we actually calculated at this point was the very, very specific situation, or the very specific probability, which maps onto the event the very first 2 boxes I open are Tiger Woods, have Tiger Woods cards in them. There are many other ways in which I can get 2 Tiger Woods cards. For instance, maybe the first 2 boxes don't have the cards. Maybe it's the first and the third. So maybe instead it was Tiger Woods, not a Tiger Woods, Tiger Woods, Tiger Woods. Sorry, not a Tiger Woods, not a Tiger Woods. Maybe the first and the third have the Tiger Woods card in them. And the second, fourth, and fifth don't. So we would have to, these are 2 different events, but in both of them we've gotten exactly two Tiger Woods cards, so we'd have to add those probabilities. But of course, there could be other arrangements. I could get, Tiger Woods, not a Tiger Woods, not a Tiger Woods, Tiger Woods, not a Tiger Woods. 0.2, 0.8, 0.8, 0.2, 0.8. And again, in each case, it's still going to be 0.2 squared times 0.8 to the third. The question is, how many of these am I going to have to do? How many of those would I actually have to write down? Because it would be 0.2 squared times 0.8 to the 3 every time. But how many are there? Because if I can figure out how many there are, I would just add that amount up. And repeated addition is the same as multiplying, so I can just, if I can figure out how many there are, I'm just going to put that number there. Right? That's how many times I would have to be writing these scenarios out. I don't have time to go through a counting lesson with you, but the way this is handled is you've got 5 different options, in other words 5 slots, and we're choosing 2 of them to have the Tiger Woods cards in them. That's how many of these I would have to write out. 5, choose 2. So that's what we put in front of our actual probabilities being multiplied. Okay, that actually counts up all of the ways that we can get exactly 2 Tiger Woods cards and 3 that are not. Alright, and so what we just did was an example of a binomial. This is a binomial probability. Okay, and what the thing you want to keep in mind is that this type of probability model will be applicable when you've pre-specified how many trials you're going to do. You're not waiting for a success. You're deciding to do a certain number of trials, and you want to see how many success, and then you decide how many successes you're interested in. In this case, we were interested in 2 successes. Okay, so to summarize on the next page, the binomial model, we have certain parameters. N is the number of trials, so in our case N was a 5. P is the probability of success and Q failure, so in our case P was 0.2 and our Q was again 1 minus P, or 0.8. And X was the number of successes in N trials. For us, X equaled 2. So in general, the probability of exactly K successes in N trials would be, notationally, the probability that X equals K, and for us it was 5 choose 2 0.2 to the, so our K was 2 squared, and 1 minus P, or Q, was equal to 0.8, and then N minus K would have been 5 minus 2, which is 3, meaning all the other boxes we opened just couldn't have a Tiger Woods card in them. And then, of course, as I mentioned before, with the probability model comes your mean and standard deviation. Which are given by these formulas here.